everyone, Lisa here. Today we will be discussing selection sort in this video. As usual, we will have some theory, then we will implement selection sort in Python. The selection sort algorithm starts by finding the smallest entry. Swap the smallest entry with the first entry. Swap. Sort this side. Unsort this side. Part of the array is now sorted. Find the smallest elements in the unsorted side. Smallest element in the unsorted side. Swap with the front of the unsorted side. We have increased the size of the sorted side by one element. Sorted side, unsorted side. The process continues. Smallest from unsorted, I will swap it. Swap with front. Sorted side is bigger. The process keeps adding one more number to the sorted side. The sorted side has the smallest numbers, arranged from small to large. We can stop when the unsorted side has just one number, since that number must be the largest number. Sorted side, unsorted side. The array is now sorted. We strictly selected the smallest element and move this element to the front of the unsorted side. Animation selection sort. I have 7 elements: 99, 45, 68, 90, 29, 34, 70. By smallest key in unsorted part of array. Min index equals 6. I will swap elements index 0 and element index 6. Continue. Find smallest key in unsorted part of array. Min index is 4. I will swap element index 1 and element index 4. Elements already in their right position. Remaining elements to be sorted. Continue. Find smallest key in unsorted part of array. Min index is 5. I will swap elements index 2 and element index 5. Continue. Find smallest key in unsorted part of array. Min index is 4. I will swap it. Continue. Find smallest key in unsorted part of array. Min index is 5. I will swap elements index 4 and element index 5. Swap. Remain element to be sorted. Find smallest key in unsorted part of array. Min index is 6. I will swap elements index 5 and element index 6. All elements already in their right position. Selection time sort analysis. In our notation, what is kind running time for an items? Average kind running time for an items. Step of algorithm. For I equals 1 to n minus 1. All n. Find smallest key in unsorted part of array. All n. Swap smallest item to front of unsorted array. Degree size of unsorted array by 1. Selection sort analysis all n square. Now I will implement in selection sort in Python. New test document. Selection .py. New dev selection sort. elements. But as usual, if name equals name elements equal 89, 45, 68, 90, 29, 34, 17. Selection sort element. Print element. I will implement n equals length element. For I in range 0 to n minus 1. Mean index equal I. For size in range mean index plus 1 to n. If element size illusion element mean index equals size. If I not equal mean index, I will swap element I and element mean index. Element I equal element mean index and element mean index equal element I. Swap element I and element mean index. Okay. I will run it. CMD Python selection.py name index is not defined. Okay. Mean index Python selection.py 13, 29, 34, 45, 68, 89, 90. Okay. If you want to see more videos like this in the future, please consider subscribing. Alright, well, that's all I have for you today. I hope you enjoy it, and as always, I hope to see you next time. Bye. Hello everyone, welcome to my channel Codewithlisa. Today we will be discussing insertion sort in this video. As usual, we will have some theory, then we will implement insertion sort in Python. Insertion sort, sorting problem given an array of n real numbers. Rearrange them so that they are in increasing order. In I iteration, read I value, repeatedly swap value with the one to its left if it is smaller. Property after I iteration, array position 0 through I contain original elements 0 through I in increasing order. I have 10 elements. Iteration 0 2.78. Step 0, no swap. Iteration 1 7.42. Step 0, no swap. Iteration 2, step 0. I noticed that 7.42 is greater than 0.56. I will swap it. So now the 0.56 came in front of 7.42. Step 1, 2.78 is greater than 0.56. I will swap it. Okay. Step 2, no swap. Continue. Iteration 3, 1.12. Step 0. I notice that 7.42 is greater than 1.12. I will swap it. Continue. Step 1, 2.78 and 1.12. I will swap it. Step 2, no swap. Iteration 4, 1.17. Step 0. I noticed that 7.42 is greater than 1.17. I will swap it. Step 1, 2.78 and 1.17. I will swap it. Step 2, no swap. Iteration 5, 0.32. I noticed that 7.42 is greater than 0.32. I will swap it. So now 0.32 came in front of 7.42. Step 1, 2.78 and 0.32. I will swap it. Step 2, 1.17 and 0.32. I will swap it. Step 3, swap. Step 4, swap. Step 5, no swap. Continue. Iteration 6, 6.21. I noticed that 7.42 is greater than 6.21. I will swap it. Step 1, no swap. Iteration 7, step 0. I noticed that 7.42 is greater than 4.42. I will swap it. Continue. Step 1, swap. Continue. Step 2, no swap. Iteration 8, 3.14. Step 0. I noticed that 7.42 is greater than 3.14. I will swap it. So now 3.14 came in front of 7.42. Continue. Step 1. I will swap it. Step 2, swap. Step 3, no swap. Iteration 9, 7.71. Step 0, no swap. Done. Another example. Move left to right through a right. Exchange next element with larger elements to its left one by one. D, R, U, T, E, F, O, R, C, E. Gray color, unsorted. Red color, active. Green color, sorted. B, no swap. R, no swap. U, no swap. T and U swap. T and no swap. E and U, swap. E and T, swap. E and R, swap. E and B, no swap. F and U, swap. F and T, swap. F and R, swap. F and E, no swap. O and U, swap. O and T, swap. O and R, swap. O and F, no swap. R and U, swap. R and T, swap. R and R, no swap. Continue. C and U, swap. C and T, swap. C and R, swap. C and R, swap. C and O, swap. C and F, swap. C and E, swap. C and B, no swap. Continue. E and U, swap. E and T, swap. E and R, swap. E and R, swap. E and O, swap. E and F, swap. E and E, no swap. Okay. Advantages. Simple, efficient for small data sets. One of the factors are and square performance algorithms do not require extra memory, low overhead, best case E or N, nearly shorted input. Disadvantages. Poor performance with large lists. Expensive with many elements. Not as quick as merge sort or quick sort. What case E or N square? Input array. List in reverse order. Insertion sort runtimes. Best case O N. Average case O N square. What case O N square. Now I will implement insertion sort in Python. New text document, insert. Py. Insertion. By. Depth insertion sort element. If name E equals to name. Elements equal 2.78 7.42 0.56 1.12 1.17 0.32 6.32 6.21 4.42 3.14 7.71. Okay, I have 10 elements. Insertion sort element. 3 element. Okay. For I in range 1 len element, then element I size equal I minus 1 y size is greater than or equal 0 and temp elixir elements size plus 1 equal element size equal size minus 1 element size plus 1 equal temp. Okay, I will run it. CMD Python Insertion copy y 0.320 and all the text element equal BRUEFORCE. Okay. If you want to see more videos like this in the future, please consider subscribing. Alright, well, that's all I have for you today. I hope you enjoy, and as always, I hope to see you next time. Goodbye. Hi everyone, Lisa here. Today we will be discussing PowerShell in this video. As usual, we will have some theory, then we will implement PowerShell in Python. Sorting text and unordered collection and match it an order one. Doubling up the largest element reverse a collection of elements. Move from the front to the end. Double the largest value to the end using pairwise comparisons and swapping. Bubble sort is one of the sorting techniques. The way it works is, let's say you have a list of numbers and you want to sort this list. You will begin by comparing the first two numbers, 77 and 42. Then if 77 is greater than 42, I will swap it. So now 72 came in front of 77, and then I repeat this process for the second and third element. So I compare 77 and 35. 35 is less than 77, so of course I will swap that, and now my list looks something like this. Again, do the same process for element number 3 and element number 4. So I can keep on doing this process until the very end. 77 and 12 swap. 77 and 101. No need to swap. 101 and 5 swap. And what will happen as a result of this process is 101, which is the highest number, will go towards the end. That's why this is called bubble shock. When you have a bubble in the water, a bubble will pop up. It will come from the bottom to up. Similarly, 101, which was the highest element, pop up from the bottom. It went on the way up to the correct position. So if you look at on, the number 101 should be in the last position because it is the highest number. Now we got 101 in its right position. Item of interest. Notice that only the largest value is correctly placed. All other values are still out of order, so we need to repeat this process. Repeat bubble up how many times? If we have n elements, and if each time we bubble an element, we place it in its correct location. Then we repeat the bubble up process n minus 1 times. And this guarantees we will correctly place on an element, bubbling on the element. N minus 1, reducing the number of comparisons. On the end bubble up, we only need to do math minus and comparisons. For example, this is the fourth bubble up. Math is 6. Third, we have comparisons to do. Already sorted collections. What if the collection were already sorted? What if only a few elements were out of place and after a couple of bubble ups, the collection were sorted? We want to be able to detect it and stop early. Using a Boolean flag, we can use a Boolean variable to determine if any swapping occurred during the bubble up. If no swapping occurred, then we know that the collection is already sorted. This Boolean flag needs to be reset after each bubble up. An animated example. Index 1, this swap, this underscore swap form, 98 and 23 swap, 98 and 45 swap, 98 and 14 swap, 98 and 6 swap, 98 and 67 swap, 98 and 33 swap, 98 and 42 swap. Finish the first bubble up. Finish fifth bubble up. We did do any swapping, so all of the other elements must be correctly placed. We can skip the last two paths of the outer loop. Summary bubble up algorithm will move a lattice of value to its correct location to the right. Repeat bubble up until all elements are correctly placed. A maximum of n minus 1 times can finish early if no swapping occurs. Now we reduce the number of elements we compare each time one is correctly placed. Let's implement this in Python now. New text document purple sort purple .by okay. That purple sort element if name equals min equal 77, 42, 35, 12, 101, 5. Purple sort element. Element. Size equal length element for I in range size minus 1 for size in range size minus 1 minus I if elements size is greater than element size minus size plus 1. Swap plus 1 equal okay. Okay. I need this swap equal false. This swap equal true. If not, this swap rich. Okay, I will run it. CMD Python purple .py 5, 12, 35, 42, 77, 101. Okay, exactly. Okay, in data structures and algorithm tutorials, this technique is covered as the most common technique for performing a sorting. It performs sorting in all n square complexity, so it is not the most efficient, but it is probably a very simple technique to understand. I hope you are thinking this tutorial. If you do, please give it a thumb up. Share it with your friend. Bye.